So today in this numerical class, we finally get numerical. Only took a few weeks. Yeah. Have what? Not in this class. Yeah, there's one oral final at the very end, and that's all. Yeah. In terms of our professors actually like to grade stuff. Okay. So, simple kind of numerical method is finite distance. Okay. Like, wow, I found a mistake in the notes already. Yeah, I think I have. Okay. So the goal of finite is to approximate some derivative. So we'll assume your function is one variable, so it's a function of x. At a given point that I'll call x naught. Using values of u at the point of interest, x naught, and neighboring points. Okay. Oh, I wonder if that's Megan emailing. No. Okay. No. Because when do we use differentiation formulas? When we have a formula for a function involved, so we can use power rule, chain rule, quotient rule, etc. But in numerical methods, we don't necessarily have that. So why is this our goal? That our only information about the function u of x generally is going to be values on a grid. So we have a grid consisting of x values, and we may know the values of u at those points and no over points. Whereas a derivative, the exact derivative of u, is where you take expression like u of x plus h minus u of x over h and take the limit as h goes to 0. That means being able to have an approximation as accurate as you would like, you would need to be able to evaluate u of x at any point whatsoever. We don't have that ability. So, this kind of approximation under these circumstances is the best that we can hope for. All right. And that's one reason. The second reason is actually a simpler one, or easier to appreciate: efficiency. Because the kind of differentiation rules that we're accustomed to using and we use all the time for computing derivatives by hand. Of course, there are many programs that implement differentiation rules like Maple, Mathematica. Now MATLAB has a symbolic toolbox, but that actually is an interface to Maple. So it's not really a separate thing. But that means representing the function as using some sort of data structure that has there's a structure of the expression that's used to define your function, taking into account operations like arithmetic operations, square roots, sine, cosine, exponential, any standard functions like that. And that doesn't really play to a computer's strengths. Computers are best when it comes to add, subtract, multiply, divide. So computing an approximate derivative using this kind of information can actually be a whole lot faster than taking a derivative this way. And sure, this derivative is exact and it's available at any point, but we have the issue of speed. Also the fact that there are many situations where using this simply isn't an option at all. But even if it is an option, it's not the most efficient way. And because if you can get an approximation that is highly accurate, like several decimal places, that's probably good enough for your purposes in most cases. All right. So we're going to assume that U has sufficiently many continuous derivatives where L is greater than or equal to J. For some reason in the notes, I have J greater than or equal to L, and I'm going to have to, well, you know what? I do this often during the class anyway. I got to check that now because that's driving me nuts. Like going back to my primary source. Find that difference. Okay. Okay, J. Yep, this typo's my fault. Oh well. At least this time, for the fourth time teaching in class, I finally kept it. Okay. Well, I just glossed over it the other times, but well, forgot to fix it. Okay, so I think what I'll do, yeah, I want to start on a fresh board for this. Besides, this one time I forgot about my glare boundary. Okay, but we need to assume that whatever derivative we're going to compute, that derivative is at least continuous, that at least have many continuous derivatives available. In fact, we might need even more generous assumption than this, depending on the kind of formula we're going to end up with, but we'll come to that later. Okay, so okay. All right, so the form of our approximation is that the jth derivative U at a certain point x naught is approximated by a sum of, that is a linear combination of the values of u at selected points that include x naught, but other points as well. And at the moment, I'm not going to make any assumption about where these points lie. Like they could, any of these xi's could be less than x naught, could be greater than x naught. We're not assuming equal spacing at this point. But I will make the assumption that all of the xi are at least distinct. Okay. All right. Now, so the idea is for a given derivative, we need to find these coefficients. Fix my writing here. Dx of j. And although this doesn't appear in the notes, what I'm going to do is I'm going to add a superscript to these AI to make clear that these are coefficients for the jth derivative that we're looking for. Because for a different value of j, we're going to have different coefficients. So the unknown coefficients that we're looking for, Aij, the name we give to those is a finite difference stencil. Okay. So stencil describes how you combine function values at various points to approximate the derivative you're looking for. All right. So to find these coefficients, we do a Taylor expansion. Okay. So the expansion will be centered at x naught. Okay. And I want to emphasize here this notation. You may have seen this before, but in case you don't remember, when we have a superscript in parentheses for a function, that refers to a derivative. So this is the kth derivative of u evaluated at x naught. Now, as a shorthand, I'm going to define xi bar to be xi minus x naught. So then, if I look at my approximation, so j derivative at x naught, which is approximated by this linear combination of function values, but then I'm going to replace this with the Taylor expansion. All right, so I'm going to have derivative, x or k factorial, and in here, xi is being substituted for x in here. So now I'm going to have xi bar raised to the kth power. And then what I'll do is I'm going to interchange the order of sums. So I'm going to have a naught a factorial, and then what I'll have here is a sum. M of Aij x I bar to k. All right, questions up to this point? So here we have a derivative at x naught, a particular derivative, J's derivative. Here we have derivatives of all orders at x naught. K derivative divided by k factorial. All multiplied by this expression right here, where these a's, i's are still unknown at this point. So we want this expression here, we want it to equal 0 for k not equal to j. Because we want this expression to reduce to just one derivative, the jth derivative. All of our terms gone as much as possible. So we want it to be equal to 0. And then we want it to be equal to j factorial when j is equal to k. Because this is equal to j factorial, it will cancel with the j factorial down here, leaving us with just jth derivative at x naught. Exactly what we're looking for. So these conditions give us a system of, well, I guess really it's infinity linear equations. In m+1 unknowns, which are A0, A1 up to AM. So of course, we're not going to be able to satisfy this for all values of k, because that would give us an exact approximation, but that's not possible when the approximation has its form. We don't have enough degrees of freedom for that. The best we can do is at least make sure that we get the correct values here for m+1 values of k. That would include k equals j, of course. And then for whatever terms that we have something non-zero here when we want something 0, that's going to be error. That's going to be error. So we consider k going from 0, 1 up to m. That way we'll have a system of equations that has a unique solution. Okay. So any questions about our system of equations here? So let's take a look at this system of linear equations that we have. what we can say now is that the stencil, let's do some coefficients, A, J, right, 0 up to M. Satisfies this system of equations. B, A is equal to B, where A is just the decimal coefficients. B is the vector that is all zeros except J plus first entry is equal to J factorial. And all others are 0. And then finally, Bij, or Bi, rather, is xi bar raised to the kth power for I and k going from 0 to m. So this is an m plus 1 by m plus 1 matrix, but for convenience, I'm indexing the entries using 0-based indexing, unlike the traditional 1-based indexing for a matrix. Okay. All right. Now, so the form of the matrix, so what it looks like is for actually check my try this backwards. Well, wait a minute. I should be the column index. Yeah, so it's BKI. Okay, so each row of this system, so rows correspond to index K in the Taylor expansion. Columns correspond to I. That's the index used for the coefficients of the stencil.
Rows are corresponding to the coefficients of Taylor expansion.
Yeah, because I had the kth derivative. Yeah, that K. So that means the first row of this matrix corresponds to K equals 0. So the first row is all ones. And then the second row would be all of your xi bars. And then your third row would be all of those values squared. And so on. All the way down to x0 bar to the m, xm bar to the m in the last row. Okay, so each row consists of the same x values just raised to increasing powers. And this is called a van der Waals matrix. Sometimes it might be described differently, like maybe the columns have this pattern instead of the rows. It depends on what source you're using. And what's known about a van der Waals matrix, that when you have all of the x values distinct, it is known that the matrix is invertible, van der Waals matrix is invertible. We're actually in the formula for the determinant of the van der Waals matrix, and it consists of all these linear factors that are differences of these values. Well, if all of these point x values are distinct, all of those differences of those x values would be non-zero, and you're multiplying them all together, so you get something non-zero, therefore it's invertible. So that tells us that the stencil is unique. So any questions about how this goes? Okay. Um, Actually, it looks like what I have here, the rest of my notes. It's nothing but examples. You can see it would not be very difficult to write a MATLAB code that would compute a finite difference stencil for you. Once you determine the points you're going to use to approximate the derivative, then you just form a van der Waals matrix, and you see the right-hand side to use. You use backslash to solve the system, and bam, there are your coefficients. Okay. Now, all right. For the first example, I'm going to let j equal 1, so we're approximating first derivative, and let m equal 1. So the value of m, 1 plus that is the number of points you're going to use. In other words, m equals 1 says we're going to use 2 points to approximate first derivative at one of those points. Okay, so in other words, we're approximating u prime at x naught by a01 u x naught plus a11 x1. So we're looking for an approximation of this form. Okay, so our stencil is a vector A consisting of these coefficients satisfies this system of equations. So the 2 by 2 matrix. So first row, and starting left earlier was all ones. And then we'd have x0 bar and x1 bar. And then here are unknown coefficients. And then the right-hand side is all zeros, except for a first derivative, the second entry is going to be equal to 1 factorial, so it's going to be 1. So that's the system of equations we satisfy. Well, sorry, what? Oh, with this?
Yeah.
Oh, that?
No, it is after that one.
Wait,
Yes.
this?
This is
Yeah, that's what I wanted the first time you said no. Is it a vector? Yeah. Yeah, because we're this is our system. VA is equal to B. Yeah. Okay.
it wasn't quite.
Okay. Okay. All right. Now, I can let x1 be equal to x naught plus h, for some spacing h. So that means that x0 bar is 0. In fact, it's always going to be x0 bar is 0 because x0 bar is x naught minus x naught. And therefore, x1 bar is going to be h. So now the system we're going to solve is so 1, 1, 0, h. Okay. Oh, whoops, that should be 0, 1, not 1, 0. Okay. So now we can easily solve the system because of the second equation is uncoupled from a rest. So that tells us that A, 1, 1, 1 over h. Is that what you're doing? You were solving a system? Okay, because I was waiting to the right time to continue, so I wasn't sure. Okay.
Oh, I was.
Okay, all right. Now, the top row says that all the coefficients must sum to 0. And that's always true in finite differences. The sum of all the coefficients in a finite difference tensor must be 0, which makes sense because suppose a function u is a constant. Then this approximation would just be the constant times the sum of the coefficients. But a derivative of a constant function must be 0, which is why the sum of the central coefficients must also be 0. So, therefore, A01 has to be minus 1 over h. So, that means u prime and x naught is approximately u of x naught plus h minus u of x naught divided by h. And this is the forward difference. Now, on the other hand, if I let x1 be equal to x naught minus h, so that means that x1 bar is equal to minus h. So I get u prime at x naught is u of x. So what happens there is you basically replace h by minus h throughout. So u x naught minus u x naught minus h all over h, and that is the backward difference. So you can see if you were to solve this system again, but replacing h by minus h, you would get the same coefficients except negated. Okay. So any questions about these two approximations? Yeah.
So I'm a bit confused about where we let x1 is equal to x naught plus h.
Yeah.
Which implies that x naught bar is equal to 0.
Yeah.
Not getting that answer.
Oh, because xi bar is xi minus x naught.
Okay.
Yeah, so it's just for convenience, we're shifting all the x values by x naught and making x naught the origin. Our question? Okay. Now, there's one thing I still need to cover about these examples, and that is what is the error? How accurate are these? And I mentioned before that when we got the system of equations, it's based on an infinitely long Taylor expansion, and so we're able to make certain terms in that expansion equal what we want, and then the rest we just have no control over because we don't have enough degrees of freedom. So those terms that we have no control over, that represents the error. So now I'm going to go back to that, and to give you an idea of what the error should be. And I'll show you for forward difference. And it turns out that the error will be the same for backward difference, except the opposite sign, because you're replacing h with minus h. So earlier, I had written that my I'll specialize to the first derivative. U prime of x naught is approximately but this turned out, Taylor expansion turned out to be equal to sum equals 0 to infinity of k derivative at x naught over k factorial times this sum. I've written it as a general sum, but I'll specialize it to this case. A 0, 1 x 0 bar to the k power plus a 1, 1 x 1 bar to the k powers. So it's what I've written earlier, except I'm now imposing that j is equal to 1 and m is equal to 1. Okay. Now, we know that x0 bar is 0. So this term is gone. And x1 bar is h. So this is a11 h to the k power. But a11 turned out to be 1 over h for a forward difference. So for forward difference, we have a11 is 1 over h. So now what we get is u prime of x naught equals sum oh, I goofed here. This is equal to 0, k greater than 0 for u. For k equals 0, it's equal x naught bar. X naught bar to the k power is equal to 1 when k is 0. All right. So, so now we have u prime x naught is approximately, so when k equals 0, we're going to have u of x naught over 0 factorial, and then I have a01 is minus 1 over h times x naught bar to the 0th power, and I have 1 over h x1 bar to 0 power plus u prime at x naught over 1 factorial, and I have minus 1 over h x naught bar to the first power is 0, and then x1 bar to the first power is h. Okay, and then I'll do one more term. U double prime at x naught over 2 factorial, so minus 1 over h times 0 plus 1 over h times h squared, and so on, and I won't go past that point. So, so what happens when we condense these terms? Well, this one goes to 0. This becomes 1. So our second term condenses to u prime of x naught, which is what we're looking for. And over here we have, okay, 0 here, but I have h squared over h, which is h. So I get h u double prime at x naught over 2. And then there are additional terms. Okay. So this gives us an idea as to what the error is. And notice as the spacing h goes to 0, so in other words, we could say that so the error is big O of h. In other words, what I'm saying here is proportional to h. So at least we could say this approximation converges as h goes to 0. The error goes to 0. Assuming that the second derivative is continuous. So this is why I meant by what I said earlier, that we need to assume that u has at least as many continuous derivatives as we're looking for, but really we need to assume more than that. Like if we're looking for first derivative, we need to assume at least 2 continuous derivatives for our error formula to be valid. So these approximations work best for smooth functions. And if I were to do the same thing with backward difference, I'd get the same result except minus hu double prime over 2. So questions about what happened here? Now, I wanted to go back to this because I mentioned earlier how whatever terms are left over give you an idea about the error, but this is not really a rigorous way to obtain an error formula. We do use Taylor expansion, so now I'm going to show you that. Just because what I'm doing here is kind of sloppy, because I'm having this approximation here, I'd rather have everything be exactly equal to each other. Okay. All right, so get error formula. All right, so we're going to assume U is in C2. So there's two continuous derivatives. So then, a forward difference, U of x naught plus H minus U of x naught over H. I'm going to replace U of x naught plus H by a Taylor expansion, but I'm going to cut it off after the second order term using a Taylor remainder. So this point C, squiggly, is between x naught and x naught plus H by Taylor's theorem. So now I go ahead and simplify this. We have U of x naughts canceling. We have U prime x naught H over H. So that simplifies to what we're trying to approximate. Prime x naught. And then what's left is H over 2 U double prime C. And sure, so that is the term that we got earlier. But I want to make you aware of a way this is customarily written. What we normally do is say, well, we're trying to approximate. That goes on the left side. Then on the right side, we feature our approximation. And then the error. So I'm moving the error to the other side. So that is our error term, minus H over 2 U double prime. And the point is it's H to the first power. So which is not great. I mean, as H goes to 0, you expect the error to go to 0, but you'd like to have the error go to 0 quickly. And this is not very quick. It's linear. For a backward difference, I would get plus H over 2 U double prime at a point between x naught and x naught minus H. Questions about any of this? All right, now I'm going to show you a few more finite difference rules. Okay, so the terminology we use, you say that this is first order accurate. Because the error is big O of H to the first power. Whatever the exponent here is, that is the order of accuracy. right, so now I'll show you some more accurate rules than first order. So I'm going to keep j equals 1, still first order, but now I'm going to let m equal 2. So we have 3 points in our approximation. And we're going to assume equal spacing. So x1 is, again, x naught plus h, x2 is equal to x naught minus h. So that means that for x0 bar, as always, 0. X1 bar is equal to h, x2 bar is equal to minus h. So to solve for a stencil, our system linear equations will be, so now it's 3 by 3 Van der Waals matrix, because we had 3 points. So we're going to have 1, 1, 1. We have x, so this would be h and minus h, finishing up second row. And then h squared, h squared. Third row, our stencil coefficients, a 0, 1, a 1, 1, a 2, 1. On the right-hand side, because it's first derivative, the second entry will be 1. All of our entries will be 0. So right of this here, yeah. So right hand side, all elements are 0 except whatever derivative you're wanting to find. That entry plus 1 is a factorial. So yeah, j factorial. Okay. I won't go through the algebra here. What we get is 0, 1 is equal to 0. So x naught, u x naught itself is not used. A 1, 1 turns out to be 1 over 2h, and a 2, 1 minus 1 over 2h. So as before, as always, the coefficients have to sum to 0. So now what we get is nu prime and x naught is plus h minus h all over 2h plus, let's see, the error in this case would be minus notice it's order h squared. And okay, this is driving me nuts. I don't have the exact error formula in my notes. I'm assuming Yes, it is right. If you look at section 9.1 in my book, that's where the error formulas derives. So this is called the center difference. Because the point at which you want a derivative is at the center of 2 points that you're using to get it. And the reason why I was able to recover the error formula was, I didn't keep in mind, like, notice that the error for forward difference and backward difference are of opposite signs. The center difference approximation is the average of the forward difference and the backward difference. So if you average those two approximations, because their leading error terms are of opposing signs, they'll cancel. So then you look into the next term of a Taylor expansion, which is h cubed over 6 times third derivative. And those, yeah, you divide by h, get h squared, and you average those error terms, which are the same, except the unknown point is different. So that's what that works. Okay, so this is a whole lot more accurate. Even though it's the same amount of work, you're evaluating a function at 2 points regardless, but you get a whole more accuracy because of the symmetry. So that symmetry can really help to get a higher order accuracy. All right. Any questions about this one? Now for another example, I'm going to let j equal 2 now. We're going to look at second derivative. Keep m equal 2, and we use the exact same points. So the matrix will be the same. It's the rest of the system that changes. One thing, my coefficients, my tensile coefficients have a superscript of 2 now because it's second derivative that I want. And also because it's second derivative I want, it's the third entry of a right-hand side b that will be non-zero now. So again, j factorial in j plus first position, but j is equal to 2, so you're going to put a 2 in the third position. But because the right-hand side has changed, the solution is going to be very different. And what you end up with is you get minus 2 over h squared. 0 of coefficient, and then here I have 1 over h squared, and again 1 over h squared. So the coefficients will still sum to 0. And now I have u double prime at x naught. So u of x naught plus h minus 2 u of x naught plus u of x naught minus h. And this will again be second order accurate, but it'll involve the fourth derivative term. So we need at least 4 continuous derivatives for this to be valid. And because I have no memory, I'm going to look up here for me. Minus a squared over 12. So second order accurate, just like, and it's also called the center difference. Because unfortunately it has the same name. So you need to make clear when you're talking about standard difference, which derivative you're talking about, or hopefully it's clear from context. And again, because of the symmetry, we have second order accuracy. Because so the higher order derivative you want, the more points you need. So for first derivative, we use at least 2 points, and it's generally going to be first order accurate unless you have symmetry, in which case you get second order. The second derivative, if you use 3 points, generally you're going to get only first order accuracy, again, unless you have some symmetry, that will give you second order. Any questions about this one? Also, as a higher order derivative you're looking for, the more regularity you need to assume for you to have to know what the error formula is. The standard difference for first derivative, we all needed 3 continuous derivatives for a second order error, but now we need 4. Now, I've shown you how to get these using Taylor expansion, but you can also derive these formulas using polynomial interpolation. So if you are using n+1 points to approximate a certain derivative, then that's equivalent to fitting you at those points with a polynomial of degree m. And then what you do is, whatever derivative you're trying to get at x naught, you take the derivative of your Lagrange interpolating polynomials and evaluate those derivatives at x naught. And that'll give you the same coefficients. And so this is discussed in my book also in section 9.1. First using a Taylor series to derive these kind of formulas, and then Lagrange interpolation to derive these formulas. Okay, now, so that's really what we're doing is to approximate the derivative of a given function f of x, you fit f of x with a polynomial of a certain degree and take the derivative of that approximation. So the approximation of a derivative is the exact derivative of the approximation, in this case, polynomial. And it makes sense to use polynomial because those are very easy to take derivatives of. But what are some other functions besides polynomials that are pretty easy to take derivatives of? That's one. What's another? What?
Trig functions.
Oh, constants followed to polynomials, but yes, trig functions. Or it's not all trig functions, though. Sine and cosine. Which are related to complex exponentials. And when we get to spectral methods later, I can take advantage of that. And use derivatives of those kind of functions to obtain different kinds of approximations than what you see here. Okay. Oh, wow, I have 1 minute. Okay. I only had one very quick example, and I was going to stop anyway. Everything I've shown you is for taking a derivative of a function of one variable, but the same idea applies to functions of several variables. So in 2D, for a higher dimension even, you use a multivariable Taylor expansion. And you can again obtain a system of linear equations to solve for the coefficients of your stencil. I won't go through the details here, but one example of that is the Laplacian at a given point, or in 2D, because remember that's uxx plus uyy. So we have x naught plus h, y naught plus naught, y naught plus h, minus 4 u of x naught, y naught, plus, run out of room here, x naught minus h, y naught, plus u of x naught, y naught minus h, all over h squared. And the error is for h squared, assuming we have same spacing h in the x and y directions. And I can, if you're drawing a stencil, this is the point x naught, y naught. Then I use its north, south, east, and west neighbors. This is x naught plus h, y naught to the east, x naught minus h, y naught to the west, x naught, y naught plus h to the north, x naught, y naught minus h to the south. But there are other ways of approximating higher derivatives like a Laplacian using different arrangements of points. Like this is called the 5-point stencil. There's also a 9-point stencil that uses the northeast, southeast, southwest, northwest neighbors as well. That would also be second more accurate. This, you can see, comes from taking the center difference for uxx and the center difference for uyy and just adding them together. And that's how we get to minus 4. Because remember, center difference for second derivative had a coefficient of minus 2 at the point where you want a derivative. So you have that for uxx, you have it for uyy, add them together, minus 4. Okay, so, and even though 9 points seems like a whole lot more work to get similar accuracy, there are actually some significant advantages to it that I'll get into another time. Okay, so there you have it, tiptoeing the finite difference. See if maybe on Thursday, after whatever I'm covering that day, if we can take some time for homework questions. And so the way it seems to go, but it's been a lot of time at the beginning covering stuff, and then later it's like, oh, well, now I got this time, I might as well ask your homework questions. So. Okay. Oh, I should, well, you should look at the hints document certainly for that. But I'll probably need to give some MATLAB pointers. So don't go hurrying into it.